So this week we've moved in out of getting all that energy we had last week we were talking about. Now we're going to talk about how that energy changes the temperature in the atmosphere and how that influences other things such as atmospheric circulations. So what are some of the causes of heat transfer? Now let's look at one of the places on the earth that's kind of hot. Uh, Death Valley. If you wonder, is one of the highest temperature ever recorded on Earth was recorded there in 1913. It was 134 degrees. During 1996, they had 40 straight days of 120 degrees and 105 days of 110. So why is it so hot there? It's about the same latitude as, matter of fact, probably Oklahoma. So you would think, oh, well, if they're so hot, why wouldn't Oklahoma be? Or why wouldn't the Carolinas be? Well, that does get a lot of solar radiation. It is also actually below sea level. So it's a little more atmosphere above it. And it's sitting in a desert. So it just gets the sun upon sun, nothing breaking it up, no clouds or anything. So interestingly, the topography causes it to be one of the hottest places on Earth. So now we're going to talk about what different things influence temperature. At first, we better figure out what the heck temperature is. All atoms and molecules move. Believe it or not, your body's molecules are constantly in motion. So, because of that motion, they have what we call kinetic energy, energy in motion. So, the more that molecules are moving, the higher the temperature is. They're directly proportional. So, in a solid piece of ice, molecules are still moving. In liquid, molecules are still moving. In all the gas around you, molecules are moving. There's also an internal energy to these molecules, which comes about between kinetic and potential energy. But how do we change this motion in these molecules? What makes it slow down or what makes it speed up? That's heat. Heat is just energy in transport. So now we can talk about temperature scales. There are three of them: Kelvin, Celsius, and Fahrenheit. Fahrenheit was the original one, and it has 32 degrees as freezing, and 212 degrees is the boiling point. However, there was another scale developed by Celsius, and from that they went into Kelvin. Kelvin is really a neat scale. It is exactly proportional to the kinetic energy of a molecule. So when you get to 0 degrees Kelvin, you wind up with no kinetic energy left in that molecule. Since we can't have negative kinetic energy, that means when you reach 0 degrees, you've literally reached a point where that molecule has stopped moving. We've gotten close, but I have never heard a report yet where there's an absolute zero that has been reached where the molecule does not move. So in this part, then we have the thermometers. They're different types. Liquid in a glass is one. We used to use mercury in it. We don't use that so much anymore. Now it's more alcohol based. And then there's the various electronic ones that are out there. They're more sensitive and they can give you very quick readouts. Literally, some of the electronic thermometers out there can read temperature changes within seconds. So that is one thing we considered when the National Weather Service puts out an electronic temperature sensor, which they do with ASOS. We wanted something that could literally see temperature changes down into the seconds. So they came up with this electronic temperature sensor. When it's sitting there adequately ventilated, it can read temperatures literally within a couple seconds of change. So and to a tenth or more of a degree. So we're constantly getting information on temperature changes with ASOS. Now, how does heat flow? In other words, what moves energy from one part of the atmosphere to another, or maybe even inside the ocean or other areas in the earth? What moves that heat? Well, it's things like temperature gradient. Uh, we've all experienced it, I'm sure, where you've had a cold front go through in the middle of winter. And wow, it was nice and relatively mild before it went through. And all of a sudden, it just gets bitter cold. Well, that is a temperature gradient literally passing you. All a temperature gradient is if you're in one location and went a distance, another direction, how quickly does the temperature change over that exact distance? The faster the temperature changes over that same distance, the higher the temperature gradient. And heat always flows in response to this. It flows towards lower temperature. In other words, the atmosphere, like it does with everything, tries to eliminate any kind of gradients. It doesn't want them. So it's always going to take heat where the temperature is higher and move it towards lower temperature. So in other words, the heat that is down by the equator, where it's much hotter than it is up at the North Pole, is constantly trying to go up to the North Pole. So how some ways heat flows? Radiation, conduction, convection, and latent heat are the four ways. So we're going to talk about those a little bit. What is radiation? We talked a whole bunch about it last week. And it's energy going literally in waves. It can move through a vacuum. It can move through objects. But it's a method of moving energy from one spot to another. And then that energy can be absorbed, and all kinds of things, as we learn, can happen to that energy. That's one method. Conduction's another. Ever watch a pot on a stove and how it gets hot? Well, you'll notice that the stove is heating it up, the bottom of that pot. So how does what's in that pot that you're cooking get hot? It's conduction. That's all that's happening. It's heat being transferred from the stove to what you're trying to cook, to the food. Various things move it better than others. For example, water doesn't actually conduct heat real well. Neither does dry sand or air really poor at it. But things like copper and aluminum conduct it pretty quick. Convection. Convection only happens in fluids. Air is a fluid. So that means that it flows along, we'll say. Water is a fluid. So what happens in that is air gets warmed by the ground and begins to rise up because it becomes less dense, lighter than the air around it. As it's rising, it cools, then it gets heavier than the air around it and sinks back down, literally making a loop. You actually see this in the bubbles that occur in boiling water. That is convection. Latent heat. Okay, when you have a gas like water vapor, when that water vapor condenses or becomes a liquid, it releases heat. The molecules were flowing faster in the water vapor than they were flowing in the liquid. So it released heat at that point. So in order to evaporate, heat must be absorbed into the liquid. So these are where a phase change occurs in water vapor, and water is the only element that has phase changes in the atmosphere. Heat is either going to be released if it's going from a liquid to a solid, or from a gas to a liquid, or heat is going to be absorbed by the water. In other words, it's going to take some energy away from something. Interesting, specific heat is the amount of heat that will raise 1 degree of some substance, 1 gram of one substance, 1 degree Celsius. And look at this table and notice water takes a tremendous amount of energy to warm up. All these other things actually change degrees much quicker. And notice that ice is much quicker than actually water, or water vapor is fairly quick relative to water. So when you have a big ocean out there, that specific heat of that ocean requires a tremendous amount of energy to raise the ocean temperature. So there's always a resistance to change. And some of these ways are listed right here. So we'll take a look at different climates. If you live near the ocean, and San Francisco is a classic example of this. Uh, the wind comes off the water, and with that, temperature doesn't change a whole lot because the ocean, no matter the amount of sunshine they get up there, which isn't always a lot, that ocean water does not change temperature very much. So what happens is all the sunshine that hits the land warms it up a little bit in the summer when we have more radiation coming, and allows it to cool a little bit in the winter. But you'll notice it is not a big change. Temperature goes all the way from what, 65 degrees here to 50 in the winter, 15 degrees. Now, come inland. Let's go to St. Louis, for example, and notice you don't have the marine. So you wind up temperatures change from here, around 35 degrees, all the way up to 80. So about 45-degree temperature change. What a difference. All because you don't have the ocean influence. So absorption of solar radiation is greater than the emission of infrared radiation at the surface of the Earth. So the Earth actually heats up during the daytime. The atmosphere, on the other hand, emits infrared radiation to space, then it absorbs. So the Earth heats the atmosphere. Here you can see all the different ways radiation comes into the atmosphere and what the different components and how much approximation each thing has. If you're under clouds, for example, you're not going to get as much heating at the surface. So each one of these things impacts it. So another part of this is during cloud development, latent heating is more important than radiational cooling and sensible heat transfer in cooling Earth's surface. What do we mean by that? Basically, all that is saying is the evaporation of the Earth, of the oceans, or water over land, is more significant in cooling down the Earth than other mechanisms. All right, we're going to look at a thunderstorm for a second here. Thunderstorm starts when the air is heated at the surface. So sun's down, shining in, heating up the Earth. The Earth gets hot enough, it begins to do convection. So we have a circulation of air going upwards. The air reaches a point where it condenses. What happened when it condenses? Heat is released. So as that heat is released, more heat is transported upwards, higher and higher in the cloud. And the more and more that the atmosphere is building that cloud, the more heat is continually released. So you actually transport a tremendous amount of heat from the ground all the way up into the atmosphere in a thunderstorm. All right, Boeing ratio is basically saying, okay, you got the possibility of sensible heating or latent heating. And how do they impact? Well, if the ground dries out, the Boeing ratio is going to become higher and higher because the bottom number on it is moisture or latent heat. So you can see how that changes with drought. And here's your absorbed solar radiation. You see there's a surplus of it with the temperatures we have down between 30 and degrees north, 30 degrees south. Above that, there's a deficit of it. So the atmosphere and the Earth are always trying to move this energy down here up here to the poles. How they do that, air mass. We've talked some about what air masses are, big masses of air, literally, that have similar temperatures and moisture. Storm systems like extratropical storms that develop when we have, or tropical systems move heat up towards the poles. Finally, ocean currents. Think of the Gulf Stream current. So this is just a quick way of looking at how the heat moves up along the east coast of the United States with the Gulf Stream and actually goes over and keeps England a little bit warmer than it would be, and also Iceland. So this imbalance in our radiation, in our temperature gradients and all, is what causes weather. If the temperature was exactly the same over the whole Earth, we wouldn't have weather. So there are factors, local radiation budget, or with where the latitude is and how much cloud cover you get. In other words, if you get a whole bunch of clouds over some area, typically very cloudy conditions, it's going to keep you cooler at daytime and warmer at night. Remember, water vapor is a great greenhouse gas. And you can see here this local radiation budget. Look how it pretty steady around the equator, never changes whole much. But notice how Kansas City, the actual radiation in July is almost the same as the equator is getting. Not much difference. Notice how much Yellowknife Canada gets. So that's why we also have the change of radiation and all influencing how temperatures change from summer is warmer, winter is much colder. And here is a daytime. So we talked about the radiation budget some last week. Well, what happens is at night, temperatures on the ground are cooling off, but there's still more infrared radiation than there is, obviously, any solar radiation because we don't have any at night. The sun comes up, oh, we're starting to get some solar radiation now. Well, if we start getting solar radiation, it's pretty quickly it becomes more powerful than the terrestrial or infrared radiation. So the ground is heating up. As it's heating, it's changing the temperature in the air, right? The molecules are moving faster, heat's been transported there, so the temperature rises. That's why it takes till mid-afternoon until the solar radiation balance, the amount coming in, becomes less than the amount going out due to the temperature rising. As the temperature rises, the infrared radiation rises as well. So there are a couple other things that impact temperatures. Snow. If you go out after a major winter storm, you can hardly see because of the albedo, the brightness from the snow with the sunshine. All that sun's energy is being reflected back out into space. That's why temperatures get very, very cold at night after a snowstorm and stay cold during the day for a while. Actually, if you look where a snow line is on a weather map many times, you'll notice the temperatures are significantly colder, even though the air mass is identical, where the snow is compared to where the snow's not. Snow is a major impact. Moisture, another impact as well. If you have a lot of moisture, it's not going to get as hot as if you don't have much moisture. Finally, we're going to talk a little bit about advection. All advection is I am taking the temperature at one point and moving it to a different location. If you have cold advection, say, and you live in West Virginia, and there's this tremendously cold air mass moving in from Canada, the air switches out of the northwest. Temperatures that were, say, up in Detroit, Michigan, are being pushed towards West Virginia. That means those colder temperatures up there are coming down to your location, and unless something modifies it, you're going to get as cold as they are. Usually things do modify it, and the other point is if the air was coming up from the Gulf of Mexico or whatever warm air advection, that air would be coming up and warming you as well. Urban heat islands, final piece here of everything. There's a lot of concrete there. There's a lot of density of people, buildings. Buildings absorb heat during the day greatly. They release it very slowly at night, so that you wind up with much warmer areas in cities than you do in the countryside. So that's why cities have much more problem in the summertime with high heat than if you lived out on the farm somewhere. So that's it, really, what I wanted to talk about. I hope you talked a little bit about that. Let me know if you have any questions.